So I think let us start today's session. I hope that my screen is visible and I'm audible. So welcome to the discussion session 3 on convection heat transfer and diffusion mass transfer. So far, we have completed introduction as well as mathematical analysis, and currently we have completed one session or 1.5 hours. So today we will be having a session. By one more session, we will be finishing this mathematical analysis, and we will quickly move on to problem discussion. And some of the cases are mentioned, like different cases of convection. Then combine pre and post convection cases, and then we will have another problem discussion session. So that we can come to an end of the pre-convection process. So today, our discussion topic is just a review of the governing equation of natural convection and the non-dimensionalization, which has been previously discussed in the last class, and then constant wall temperature case and constant heat flux condition. How does that differ? What is the difference between the analysis and the difference in the analysis? So it is actually a very broad topic. So we'll be discussing most important of this. So it's very important in the of natural convection. Then natural convection that is happening with a different orientation. That is the third aspect. Okay. So today's session we will be having today's session. I hope I'm audible. Am I audible, right? Okay, anybody? I'm audible, right? Okay, I think it's okay. I'm audible. Okay. So, okay, so you can interact and have the session, so no problem. Yeah, if you have any questions or any doubts in between, you can ask. Okay, you can unmute yourself and ask. So then we will study natural convection in different orientations. So what is the impact of that? That also we can learn. So today's sessions will be a short session discussing about this, and we will discuss some few problems and we can wind up for today. Okay. So as discussed previously in the last class, please have a discussion of this governing equations. The continuity equation, which is actually shows that this condition is a mathematical equation representing a 2D incompressible flow. One more thing is missing, that is steady. It's a 2D incompressible steady flow continuity equation. Okay. So which states that dou u by dou x plus dou v by dou y is equal to 0. Okay, this is in the Cartesian coordinates. In cylindrical coordinates, it will change to du by dr plus 1 by r dou u by dou r equal to 0. That's in cylindrical coordinates. You can see. So both analyses are different. So in cylindrical coordinates, the coordinates will be r, theta, and phi. So in axisymmetric case, the variation of any quantity with respect to phi will be 0. Any quantity x with respect to phi will be 0. Okay. So that is the continuity equation. Now, next is our momentum conservation equation, which is from the Navier-Stokes equations we have derived. So these are the convective terms. U dou u by dou x and V dou u by dou y. And what is this term? This is our body force or the buoyancy term. And this is our viscous term. So this is the momentum conservation equations which have been simplified from our Navier-Stokes equations. Then comes the energy conservation equations. Okay, so which states that this is the temperature gradient. So it's due to the transport of the fluid. And this is the, sorry, this is T. That error you should note that is T, dou square T by dou y square. Okay, so this is the diffusion part. So you should be very clear about all these terms. What is alpha? Alpha is the thermal diffusivity. Okay, so that's all the basic. From that, actually, we have non-dimensionalized. Actually, some of you has, I think some of you have some doubts regarding this non-dimensionalized. So it should be thought of as converting our set of equations. So if we have a set of equations, what will we do? We will actually non-dimensionalize using non-dimensional numbers, which actually physically represent what is the flow property, what is the thermal property, etc. So it's a basic strategy of converting our equations into non-scalable types. Okay. We will discussing one problem. Why is that important today? So let us see why is it one small problem in the end. So if we look at that, so as I discussed before, U reference, which is actually this part, it is actually from the non-dimensional part. U reference can be obtained from this, that this should have the same dimensions of the numerator. So U reference square can be approximately written as G beta Ts minus T infinity into L. So in the natural convection process, we know that fluid flow happens. So I think I have in the first session, I have discussed how does that velocity profile would look like. So it will asymptotically reach here. So if this is our U infinity, or it's not, there is no U infinity in natural convection, only there is U reference, because we are not supplying any free stream velocity. Okay. So this is the U reference condition. Okay. So that is the reference velocity. So what is that? This is at a particular, for a particular length L scale. So, okay. So the profile is actually different. Okay. So this is the reference velocity, which is used to compare that with U infinity in forced convection. So in Reynolds number, we know it is Vd by nu. So here in this, we will have to write this U reference L by nu, or VL by nu in Reynolds number in forced convection. But here we will be using U reference L by nu. Okay. So using that, when we substitute that, we will be getting the Grashof number. See the non-dimensional steps that is being used. X bar we have replaced by X by L. Y bar Y by L. U bar, it is U by U reference. And V star, which is V by U reference. Then T star, that is actually having a slight deviation, T minus T infinity by Ts minus T infinity. A similar kind of approach you might have seen, this T minus T infinity by Ts minus T infinity. Anyone? Have you seen somewhere this T minus T infinity by Ts minus T infinity in somewhere in heat transfer? Anybody knowing that? Somewhere in heat transfer problem, you might have gone through this heat and mass transfer. If you know, you can leave it in the chat box also. Anyone? Is Akshay present? Alvin, Arjun, Okay, I think some are muted. Danish, have you seen? Yeah, one somebody have replied. Yes, thermal boundary layer problem. Okay. Okay, fine. That's good. Any other answer? If other than this thermal boundary layer formation, have you seen this somewhere else? Okay, I think I'll say that. So it's our 1 second. So in our lumped system analysis, I think you are familiar. Lumped system analysis. So in lumped system analysis, what we will approach if the body is there, we'll assume every properties in the body is only a function of time, all the thermal properties. It's not a function of space in the body. So there, what we will do? We will just write lasix. Suppose if the body is initially at a temperature Ti and the ambient condition is T infinity, and we need to determine the temperature of the body after some time. So what will you do? This T minus T infinity by Ta minus T infinity is equal to e raised to minus Ha by rho Vc into T, where T is only a function of time, not a function of space. Here, you see that temperature is a function of thermal boundary layer is mostly existing in which direction? In our x direction or the vertical direction. So you can even treat this as a transient problem also. But in all our analysis, we have taken steady state problem. Okay. So if you are not familiar, you may be coming with this things recently. Okay. So today our new topic that we'll be discussing is natural convection with constant wall temperature. So there are basically two conditions. One is constant wall temperature. One is constant wall flux or heat flux. Heat will be supplied at a constant rate. That is constant heat flux. If the temperature is held constant, that is constant wall temperature. Okay. So how does the heat temperature remain the same? Suppose if a body is set, if the temperature is to be constant, what should happen? Whatever heat supplied should be equal to the heat leaving, as done in our problems. So steady state condition. Whatever heat comes out is heat leaving. There is no internal heat generation happening. Okay, that's the condition. So then we are keeping the temperature to be held constant. So I have shown a figure here. Suppose we may not be able to possibly keep all the surfaces together when there is a thickness delta T or some delta TH. There will be obviously conduction happening. Then if the temperature is 50 degrees Celsius here, due to conduction when it reaches, it would reach 10 degrees Celsius here. There will be a drop, isn't it? So in most cases, like if it is a constant, like that wall should be as thin as possible. So if the temperature here is kept constant, suppose we say maybe ice pack or something, we'll keep the temperature. We can assume that to be a temperature to be a constant, isn't it? So that understanding has to be there. Okay, so just have a brief understanding of that. So TW is constant. So when heating happens, TW is constant. There will be formation of a boundary layer. Okay. So always note that these boundary layers are very thin. Don't consider them to be too thick. It will be very close to the surface. Yes. So, um, so in this case, the laminar boundary layer thickness and thermal boundary layer thickness will be there. In thermal boundary layer thickness or delta T, uh, you have to observe that it is proportional to height. If this is the height of the plate into Rayleigh number raised to minus 1 by 4. These correlations can be easily derived from the previous expressions. So I leave that as an assignment to these expressions can be derived easily from the previous thing. So you should note that delta T is HRH raised to minus 1 by 4, the boundary layer thickness. That is for actually high Prandtl number fluids. High Prandtl number means maybe greater than 1 or 200, that range, in the range of that or more. But when it comes to lower Prandtl numbers, then this becomes significant. Okay. Please note that this is minus 1 by 4. So the Prandtl number term also forms it. So delta T, which is this boundary layer, thermal boundary layer thickness, is actually a function of H as well as Rayleigh number raised to minus 1. This Rayleigh number contains our Grashof as well as Prandtl number, right? Okay. What is expression for Rayleigh number? It is G beta delta T H cube by nu into alpha. So the thermal boundary layer thickness is proportional in this range. Okay. Now let us see what will happen if the natural convection is happening with constant heat flux. So how can we ensure this constant heat flux? Suppose there is a wire and we wind this cylinder with this wire and we are supplying electric power or something. Yes, any question? Okay. So in such cases, okay. So here you should understand that Q bar is constant. But in the previous case, actually we saw that the temperature of the wall is constant, right? But here, temperature of the wall is a function of the height or y. Suppose if h is the height of the plate. Here, the temperature will be some T1. It will be T2. It will be T3. It will be T4. So temperature of the wall is not a constant. So it is actually, if you draw the lines, it may be temperature will be different at different points. But the heat flux is constant. To supply constant heat flux, the temperature is adjusted at several points. So it is temperature is actually distributed around a surface, right? Okay, temperature is a function of y, or we can write this also Tw minus T infinity, just adding a constant if the ambient temperature is constant. That is also a function of y. So unlike in the previous analysis, the thermal boundary layer thickness will be proportional to minus 1 by 5. Previously in constant wall temperature, the thermal boundary layer thickness was proportional to HRH raised to minus 1 by 4, constant temperature. Constant flux case, delta T is proportional to HRH raised to minus 1 by 4. For low Prandtl number fluids, just substitute the Prandtl number. So that also comes into picture. So at the wall and all, we can see Qs dot, which is equal to K into, by Fourier's law, K delta T by delta T, right? So delta T can also be written as K delta T by Qs star. We can substitute it back it here and we can get the modified expressions subsequently. Okay, so the delta T here is proportional to 5th raised to 1 by 5. So that modifications are there, just you can substitute and see these expressions have been obtained. Okay. So Q dash is actually minus k into dt by dy. Then Tw minus T infinity, also we can write Q dash by Yk. So generally Grashof number in constant wall temperature, this is Tw, we can write like this. But in case of constant heat flux, we have to modify the Grashof number like this. Grx. Okay. So there these terms would come. You can just substitute and see these terms. Just rearrange and see. With our condition that Q star is Q star is equal to K delta T by delta T. Because if delta T is the thickness of the boundary layer, conduction conditions are happening, you can substitute and see. It's to be noted that then the Nusselt number is a function of, hello? Yeah, any questions? Okay. So for constant heat flux, the Nusselt number is a function of Prandtl and Grashof raised to 0.2. And constant wall temperature, that is Prandtl into Grashof number raised to 0.25. As I said, it is 0.25 1 by 4 and this is 1 by 5. That from that relation itself. So Nusselt number, which denotes how much heat is transferred, can be obtained from this relation. So just have a visual of that. Just see this picture. The flow is happening, natural convection. So this is an isothermal wall. So the temperature of the wall is kept constant. So you can see the thickness of the thermal boundary layer, which actually determines the heat transfer from the surface, is proportional to y raised to 1 by 4. What is y? Y is the thickness. So the thermal boundary layer thickness is growing, or it is increasing as with y increase. You can see the growth is happening. So here it will be this thing. Some after that it will be somewhat thicker. So it becomes thicker. And finally it reaches the free stream and outside quiescent conditions. So T infinity is the outside condition. But just have a close look. So here what will happen to the flux? The flux Q double prime is not constant. Only T star is kept constant. Tw is kept constant. So the Q double prime or the heat flux has to decrease at a rate like this, y raised to minus 1 by 4, so that the delta T would remain in a constant. Delta T is constant at everywhere. So the flux has to adjust itself. But come to this uniform wall heat flux. So here Q double prime is constant. See, it is constant, you can see here. At that time, what should happen to the temperature? The temperature should vary like this. It should increase. Raised to 1 by 5 pattern. So this is coming out of the expressions in the pattern, that 1 by 5 ratio. So Q star is constant. See, the delta T is 1 by 5. So the temperature has to decrease at a rate of, or change at a rate of 1 by 5. Delta T is proportional to 1 by 5. So correspondingly, that is affecting the delta T. Okay. So that understanding should be there. So the images are showing the effect of the thermal boundary condition on the natural condition. So if you are giving a constant wall temperature, it is different. So there are basically two boundary conditions which are generally called as, one is Dirichlet condition. Second one is Newman condition. Dirichlet condition, we will specify the temperature at a particular point. The Newman condition, we will specify the flux at a point. If you are interested, you can see how that is given to several systems. Dirichlet condition and Newman conditions. These are the general boundary conditions we will be using to solve a particular system. So we'll be specifying the temperature or the heat flux at the boundaries to solve a system of equation. Okay. So let us have a look at how this natural convection is varying in different orientations. Okay. So this is a plate which has been kept inclined to the horizontal or vertical by an angle theta. The outside fluid temperature is T infinity. So here observe the pattern. So what happens is, as shown, it's a top surface of a cold plate. So what is happening here? The boundary layers are forming like this. Before that, just have an observation. Like in the previous class, I have said, if this is a heated plate, this will be the pattern of the boundary layer formation. But what if this is Ts greater than T infinity? What if Ts is less than T infinity? How would the shape of the boundary layer be? Obviously, what will happen is, if Ts is less than T infinity, all the fluid particles which are in immediately contact would settle down. So this will be the pattern. This is cold plate. Because that would happen is descending of the fluid layer. Here it is ascent of the fluid layer. Okay. So similarly, you can observe patterns like this, formation of the boundary layers. The fluid layers will be in contact and they will be settling down in a pattern. And here you can see these two are different orientations of the plate with different surfaces kept in particular directions. Maybe cold surface in the first case, it's the top surface of the cold plate. So here you can see the boundary layer is settling down. Here, what is happening? There is a rise of the boundary layer. So the bottom surface is somewhat cold relative to this surface. So that has resulted in. So why this shape difference between these two? Because we know that it is a gravity driven flow. So in the energy equation, you have seen there is a G beta T minus T infinity term. So when the fluid is kept inclined, what will happen? You shouldn't use the G term because that was for the vertical plate. Now when the plate is kept inclined, we need to use the G cos theta component. Theta is the angle shown like this. So cos theta component is the adjacent angle. G will be acting obviously in this direction. Theta is this. So G plays an important role. G cos theta and G sin theta. So along the plate, that will be acting as cos theta. So observe similar patterns, so they are different. Okay, in these cases, we will be using the G term during the ascent. Okay. Similarly, other plate Ts, you can see T infinity. These are coming like fluid layers, so they are settling. And similar with other heated surfaces, you can observe what is the pattern. There is bottom surface of the fluid layers are coming and ascending like this. So for each orientation or each arrangement, please note there is a difference in the correlations. Nusselt number average, this NUL bar is average Nusselt number. Average Nusselt number is a function. Nusselt number can be defined at a particular location. So when it is varying with respect to different location, you can calculate the average Nusselt number. Okay, we have defined average heat transfer coefficient. Like suppose it is mathematically denoted as h dx by integral dx. Okay, similarly, Nusselt number will be this for different ranges of Rayleigh number. So first you need to identify what is the Rayleigh number for the configuration, and identify this, then come to the correlations. Okay, similarly, these are the correlations that are obtained for the lower surface of the hot plate. So for different surfaces, we have to apply different correlations. So please note that. If the surface of the hot plate is facing downward, this is different. If the hot surface of the plate is facing, it's different. So that all depends upon combination of that is significant in relation to problem. Because all these are G-driven flows, gravity-driven flows. Okay. So another case is development of a plume. It is called as a plume. This region is called as a plume. Suppose if you light a candle, there will be ascent of the air. So there will be a plume region which will be created. So when a air gets, if the cylinder is heated or cooled, this is a heated case obviously because it is the ascent of the air. So ambient fluid is T infinity. So what happens is these are the boundary layers created. So based on the boundary layer thickness, our Nusselt number correlations can be obtained. So if theta is actually measured in this direction, the anti-clockwise. So at theta equal to 0, the Nusselt number is this. At theta is equal to pi by 2, which is at this point. So theta, this is theta equal to 0. This is theta equal to pi by 2. A, B, C. This is theta equal to pi. So theta is minimum at this location. After which there can be a flow separation or there's a reduction heat transfer. So theta equal to 0, the heat transfer or the Nusselt number is maximum. So as you go down, that heat transfer is minimized. So if somebody asks you when a fluid flows around a heated cylinder, where is the heat maximum or the heat transfer will be maximum? That will be obviously at this point of contact. As soon as it flow develops around the cylinder, there is a reduction in the heat transfer because the flow separation can happen. So several correlations have been developed. One important correlation is Nusselt number is equal to C RA raised to Rayleigh number raised to N. So free convection different cases have been shown. So please note that these Rayleigh are defined on diameter. So when you write the expression G beta delta T, that will be d cube by nu alpha. Generally it is L or it is called as the characteristic length LC. So for different Rayleigh number, which actually depends upon our influenced by our D value for a given T infinity and value. So for different Rayleigh number, several relations are expressed. So if you are able to conduct several experiments and study what is the effect of the changing the diameter, you can see. So for higher Rayleigh number, this C and N are larger. So with larger diameter, there will be like more heat transfer due to the formation of the boundary layer in free convection. Now in the case of concentric cylinders, so concentric cylinders, you can see there is an inner cylinder and an outer cylinder. So the flow pattern you can observe. So heated and as you see the plume, but there is no flow space. So Ti is more, Ti, To. So as soon as it reaches here, the fluid pattern which gets cooled and it reaches here, then again it rises, it gets heated, it gets cooled. So this pattern is actually continuing like this. So that is happening due to free convection. You can see in case of heat exchangers filled with PCMs and all, phase change material like wax, this kind of internal convection is happening. So don't think that it is actually only air is responsible for the free convection in another fluid, any fluids. which is in the fluid state, like this free convection happens. So that is a density should be driving the flow. Density should be driving the flow, then that is the condition. So if in a case of a PCM case, the PCM would melt, maybe wax, you can see paraffin wax or something that would melt, finally settle down and they can recirculate together. So their conduction is not only playing, convection also plays a part. So convection will dominate after. So after a lot of time, what will happen? All the PCM would melt and it would stably settle at down. So initial part will be totally dominated by conduction. So in case of paraffin wax and all, thermal conductivity is very less, maybe in 0.1 or something. But its latent heat is very high. Okay. So heat transfer equation, this is a basic equation that is obtained from our Fourier's law in conduction Q 2 pi L K by effective delta T by ln Rho by Ri. But since this is a convection dominated, you see that effective conductivity of a fictitious stationary fluid, maybe if you see wax, will transfer the same amount of heat as an actual moving fluid. So we are going to substitute this K effective. So when convection is happening, K is not pure K thermal conductivity. It will be K conductant plus convection effective. So that correlation is given here. It's a very important correlation. It states that K effective by K is 0.386 into Prandtl by 0.861 Prandtl raised to 1 by 4 RAC raised to 1 by 4. So the characteristic length LC will be, which will be used in the Rayleigh number, should be this value, this RAC, because RAC is G beta delta T LCQ by nu alpha. That LC value should be used in this type. And the Prandtl number range should be satisfied within this scale. Okay. Okay, that's all for the today's discussion. We will discuss 2 questions and we can wind up for the day. So the question is, consider natural convection. Consider natural convection heat leak from a life-size room with 3-meter wall is the height. Exposed to cold ambient, maybe which may be 10 degrees Celsius. And the question is, if the room circulation is simulated in a small laboratory apparatus filled with water, how tall should the water cavity of the apparatus be? So we know that in manometers, we use air as the fluid. What will happen? Anybody? Why don't we use air in manometers as a working fluid? Anyone? You can leave it in the chat box also. No problem. Question is, why don't we use air as a working fluid in manometer? What is the problem? Usually we use water or mercury. Why can't we use air as a manometer? Yeah, correct. So Arjun, it's correct. So the length of the tube is very large. So good. The length of the tube is very large. So if you need to use, if you use similar kind of, we need 10 meters of, to measure 1 atmosphere pressure, we need 10 meters of the manometer height, 10.3 to be perfect, to measure the 1 atmosphere pressure, which is not possible, 10 meters. So if you are changing the working fluid, we can do it very conveniently. Okay. So the room air temperature is given. So what we are going to do is we are transporting the situation into a lab scale. So obviously our objective should be, we estimate that or presume that this, if this is H dash should be less than H. Otherwise there is no use in conducting this boundary. So that advantage should be there. We are effectively changing from here, what is the fluid? Air is the fluid. Here it is water. So how will we actually get this height? So in this case, we can assume the Prandtl number is of the order of 1. Like water, we are using water, nothing filled with water or any other fluid. Even if water, we can use any other fluid also. So the criteria is, then comes our non-dimensional numbers. Use of non-dimensional numbers. So in natural convection, which is our critical non-dimensional number, what is important? Because it's Rayleigh number. Now in this problem, we will be defining Rayleigh number based on this height h. So in the question, here you should note that it is 25 and outside is 10. The question, it is mentioned that laboratory apparatus, the temperature difference between the water body and the inner surface of the cooled wall. So here temperature we don't know, here we don't know, but delta T value is 10 degree Celsius. Ti as well as To. Okay, so we are going to match air with water using Rayleigh number. Okay, so Rayleigh number based on H is G beta delta T HQ by nu alpha. So assume if this is a constant uh, temperature wall case, what is delta T, which is proportional to H RH raised to minus 1 by 4, because constant heat flux condition we haven't mentioned. It is said in the question that only this delta T is actually constant wall temperature can be assumed. Okay. Or if it is supplied by some kind of a constant flux, then you can assume then the delta T will be different, HRH raised to minus 1 by 5. So currently it's not our question. Okay. So air domain, we can calculate the RH. So uh, first we can calculate this value G beta by nu alpha, which are the thermal properties at the bulk fluid temperature. So TF, maybe we can see at a particular bulk fluid temperature. From the properties we can calculate. So that comes to be, this value comes to be 107. This G beta by nu value is actually G beta by nu alpha comes to be 107 centimeter per centimeter cube Kelvin. Okay, please note the unit. Then delta T, that is actually between the room and the outside, that is 25 and 10. So 25 minus 10, H is given 3 meter 1. So 3 meter, we need to convert it into centimeters. So 300 centimeters. 15 into 300. Okay, that's for air. Now in lab apparatus, we will be using water. So RAH is G beta by nu alpha delta T H cube. Okay, so we will assume the same mean fluid temperature and calculate this value for water. Okay, so that value is coming to be 14.45. Okay, uh, into 10 raised to 3 into delta T is 10. into H cube. So you see 14.45 into 10 raised to 3 came. So if these both should exhibit the same characters, then their Rayleigh number should be matching. So if our studying process is natural convection and we are studying the natural convection process, then this RAH, maybe we can denote it as dash. RH dash should be equal to RH if it has to exhibit the thermal characteristics. So we can write as 14.45 into 10 raised to 3 into 10 into H cube, which will be equal to 107.15 into 300. Solving that, we will get the H value to be 66 centimeters or 0.66 meters. So to study that, a 3-meter room, any thermal properties, we can replace that air with water, fluid change. And here the height is only 66 centimeters. So that is actually easily convenient. So this problem was to understand that importance of that Rayleigh number. Okay. Next question, last question. So the question is, thermal conductivity and surface emissivity of a material may be determined by heating the bottom surface and exposing the top surface to quiescent or stationary air, and temperature of the surroundings is given. So the remaining surfaces are insulated, 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 insulated. Top surface is exposed to ambient air. Okay. So the sample thickness is given to be 25 mm. It can be an electronic chip or something. And it has a platform width W equal to 250 mm. So experiment is under steady state condition, maybe studying the temperature or something. Okay. And measurements are made at lower and upper surface. So maybe at here and at the bottom surface. And it shows that here the temperature is 150 degrees Celsius. And maybe here it is 100 degrees Celsius. So this is actually wrong because heating is from the bottom. So here the temperature has to be higher. So I'm rubbing that. So here it is T1 150. Top it is 100 degrees Celsius. Power input is given. It is 70 watts. So question is, what are the thermal conductivity and emissivity of the sample? What is the K as well as epsilon value? Okay. So how will you approach this problem? So what we know is width and thickness are known. Rate of heat dissipation is known. Temperature of the quiescent air is known. So we assume steady state 1D conduction in the sample. Conduction is happening only in the vertical direction. And the sample is small relative to the surroundings. So we assume it to be a small, if this is the sample, and surroundings to be very large. So there will be equilibrium, or it will reach the steady state in a very fast manner. So there won't be much effect of this temperature change on the surroundings. So even if the temperature changes by maybe delta T equal to 200 degrees Celsius, that won't much affect the outside T infinity. That's the significance of this assumption. So when the sample is small relative to surroundings, T infinity remains constant. Okay. And assume that all heat up power dissipation is transferred through the sample and the constant properties exist. Okay. We will be using the constant thermal properties, mu, rho, Cp, etc. values. Okay. So from the tables HMT book, we can, for air at bulk fluid temperature is equal to T surface plus T infinity by 2, which is at the top surface, it is 100 degrees Celsius. So 100, 273 plus 100 in Kelvin plus 273 plus what is ambient 25. So by 2. So that is 335.5 Kelvin. At this temperature from HMT data book, we need to determine the new K alpha PR beta, which is a thermal expansion coefficient. In the question, we have to find out K of the solid. Okay, this is K of air, which is a fluid in natural convection. So straight away, without going to convection, we can determine the thermal conductivity. So the sample is here, 150 degrees Celsius here, 100 degrees Celsius here. This thickness is given to be 25 mm. So from Fourier's law, we know Q equal to minus Ka delta T by delta X. So power is actually given in watt. So Q dot. So that is P electrical power is equal to K into A. A is actually 0.25 into 0.25. Its area. 25 mm thick and width. So delta T is 50 and delta X is that along the height. So just we can simply determine the thermal conductivity, which is 0.56 watt per meter Kelvin, less than 1 for that sampled solid. Now we need to determine emissivity. Before that, let us see what are these values. K alpha, you can check it. New value comes to be 19.5 into 10 raised to minus 6. K value comes to be 0.0289. 27.8 into 10 raised to minus 6 is alpha. Prandtl number is 0.7034 for air. And the thermal expansion coefficient at this temperature, which is 1 by Tf, which I have calculated. So that is 0.00298 per Kelvin. Okay. So what is happening is, so in this process, every process is happening. Conduction, convection, radiation. So if you take the top surface, there is no conduction. Conduction has happened from here to here. From here it is convection plus radiation. So total whatever heat electric power is supplied. So it's in a steady state. So still 70 watts is coming. And that will be going through Q convection plus Q radiation at the surface from the energy balance equation. Okay. So we will be writing the equation. So emissivity, I am just simplifying that. You can rewrite that. So we know P electrical is equal to Q convection plus Q radiation. Q convection, how will you determine? H into T 2 minus T infinity plus sigma epsilon into sigma into from Stefan Boltzmann law T2 raised to 4 minus T infinity raised to 4 into W square or the area square. Okay. So rewriting that, because T2 we know at here 150, here it is 100 degrees Celsius. So T2 is 100 degrees Celsius. T infinity is 25 degrees Celsius. From that, we can just write epsilon equal to P electrical by W square minus H bar into T2 minus T infinity by sigma into T2 raised to 4 minus T infinity raised to 4. Okay, just we need to determine this H bar and we will be getting the answer for epsilon or the emissivity. So H bar is due to natural convection. So in this problem, we need to determine the characteristic length Ls, which will be using in determining the Rayleigh number. So that comes to be W square, which is the area by perimeter is 4W. So if it is a W by W surface, Then area will be W into W, and perimeter would be 4W. So that comes to be W by 4, which is 0.0625 meters. Then Rayleigh number equal to G beta delta T LS cube by nu alpha. So these are the properties of air. Delta T we know, G beta everything we know, LS we have determined. So that comes to be 9.86 into 10 raised to 5. Okay. Then H bar will be Nu L bar into K by L. Okay. So Nu L bar is the average Nusselt number. Based on this configuration, the heated plate configuration, you have to see which correlations to be used. I'll just write the correlation. Just check it with what type it matches. So the correlation is 0.54 RAL raised to 1 by 4 into K by L. So what is this K? This is K of air. Never substitute the K of the solid we have determined. Okay. Don't make that mistake. So from that, we will be getting H bar equal to 7.87 watt per meter square Kelvin. So just we need to substitute in that previous expression, epsilon equal to 70 by 0.25 square minus 7.87 into 75, the whole divided by 5.67 into 10 raised to minus 8 into 373 raised to 4 minus 298 raised to 4, which is comes to be 0.815. So emissivity is less than 1 always. Okay. So the question another could have been like this. If H bar you take it wrong, somehow you have chosen a wrong configuration. What would have happened to epsilon in determining? You have to see that you just try in a different configuration and see. So it can be observed that if you change H bar in 10% level, suppose if it is 7, if you change by 10%, which may be 7.7, if you increasing, you took instead of H bar equal to 7, you took that to be H bar equal to 7.7. You should see that epsilon will change from 0.8 to 0.9 in this case, 0.1 difference. If somehow you do the calculation and it comes 1, which means that epsilon equal to 1, that means perfect emissivity. So so you need to be very careful in choosing this H bar value. So that's important of natural convection there. Okay. So I hope that is clear. In the next session, we will be going to discuss about the flow between parallel plates. Two plates are kept together. What will happen? How will we analyze that? Okay. Then mixed convection case, which means force press free convection. Then advection or rolling, just a brief discussion of that. Then rectangular cavity like this. If it's in a cavity, how would the flow be? Like how that flow would change. Then the RB cell or Rayleigh-Bernard convection cells, how they are formed, why they are important, etc. Then brief discussion on similarity solution for natural convection. With that, we can wind up the natural convection basic parts. And these are the special cases. Okay. So if possible, we can combine that and obviously reduce our sessions. Let us see if time permits. So after that, we'll be discussing some problems. Okay. That's all for session. If you have any doubt, you can ask me. Okay, try solving problems and just be familiar with all these topics. It's a interesting topic, heat transfer, natural convection. It's a free process. There is no energy involved. So understanding these processes would be much more useful in energy efficient projects and okay, cooling of chips or many things. This would be very useful. Hope that is clear. Okay, then we will wind up for today. Thank you. See you next Sunday. Yeah.